Hello and welcome to this screencast on how to identify different chemical environments in NMR spectra. Being able to identify different chemical environments in molecules is very important for interpretation of NMR spectra. Each different chemical environment of hydrogen, carbon or any other NMR active nucleus will give a different peak in the NMR spectrum. The number of different environments is due to the symmetry, or lack of symmetry, in the molecule. The three protons in a methyl group are all equivalent to each other, as they're all in the same spatial relationship to other atoms in the molecule. The protons in most, but not all, CH2 groups are also equivalent to each other. The exceptions are where the CH2 group is in a system with constrained rotation, for example when it is in a ring or attached to a double bond. Let's look at some basic examples. Bromomethane contains a CH3 group, attached to a bromine atom. All of the hydrogen atoms on the methyl group are one bond away from a carbon atom, and two bonds away from the bromine. Therefore, they're all in the same chemical environment and would produce a single peak in the proton NMR spectrum. Bromoethane contains CH3 and CH2 groups. If we look at the methyl group first, all three protons are one bond away from the CH3 carbon, two bonds away from the CH2 carbon, and three bonds away from the bromine atom. Therefore, they are all in the same chemical environment as we would have expected. The protons in the CH2 group are all one bond away from the CH2 carbon, two bonds away from the CH3 carbon, and two bonds away from the bromine atom. So the CH2 protons are in the same chemical environment. However, the CH2 protons are in a different environment from the CH3 protons, as they're different distances from the bromine atom. Bromoethane has two different hydrogen environments, and there would be two peaks in its proton NMR spectrum. The symmetry, or lack of symmetry in molecules, affects how many different chemical environments there'll be in the molecule. Let's look at the example of butane. There's a plane of symmetry in the middle of butane, so one half is the mirror image of the other. This means that the protons in the two methyl groups are all in the same chemical environment, and the protons in the two CH2 groups are all in the same environment. There are only two different chemical environments in butane. If we look at 1-chlorobutane, where a chlorine substituent is attached to carbon 1, then this alters the symmetry of the molecule compared to butane. Now, no plane of symmetry can be drawn through the molecule, and there are four different hydrogen environments. The CH2 next to the chlorine atom is different to the CH2 two bonds away from the chlorine atom, and so on. Although we've only looked at hydrogen environments here, the same principles apply to carbon and any other NMR active nucleus. Here are some practice questions for you to try. The answers are coming up, so you might want to pause the video while you have a go. In the first molecule, 2-chlorobutane, there is no plane of symmetry. Therefore, the hydrogen and carbon environments in each part of the chain are different from each other. That means that there are four different types of hydrogen and four different types of carbon in this molecule. The next molecule, 2,3-dichlorobutane, has a plane of symmetry down the middle. This means that the number of environments is reduced. The two CH3 groups are in the same environment as each other, and the two CH groups are also in the same environment as each other. So 2,3-dichlorobutane has two hydrogen environments and two carbon environments. Methyl propanoate has no plane of symmetry, and all hydrogen and carbon environments are different. There are three types of hydrogen and four types of carbon. Diethyl ether has a plane of symmetry through the oxygen atom, so again we have two different types of hydrogen and two different types of carbon. Propene is a slightly trickier example. You might look at the molecule as it's drawn and think that there are three types of hydrogen and three types of carbon. However, that's not the case. If we look at the 3D structure, it will help to explain. Here's the 3D structure of propene with the methyl group on the left and the CH2 group on the right. If we look at the two hydrogen atoms in the CH2 group, one is cis to the methyl group and one is trans. This means that they're in different chemical environments as they have different spatial relationships to other parts of the molecule. Therefore, propene has 4 hydrogen environments, not 3, and 3 carbon environments. Finally, 2,2-dimethyl-pentane has 3 methyl groups attached to the same carbon atom. These methyl groups are chemically equivalent to each other, as they're all 1 bond from the carbon atom, 2 bonds from the CH2 group, and so on. This means that 2,2-dimethyl-pentane has 4 hydrogen environments and 5 carbon environments. Thanks for watching, and look out for more content coming soon on the Analytical Science Tutor channel.